Next speaker is an interactive team led by Dr. Fabian, Isensee, and Max. Uh, so Dr. Fabian is the head of applied computer vision lab in DKFZ. Max is doing his PhD at DKFZ and also an obvious rising star in this field. Since most of the audience have background on medical image segmentation, I don't think I need too much words to introduce Fabian. One sentence is enough. This is Fabian. But I still want to share one point that latest young students may not know, but should know. Most students know nnUnit was published on a prestigious journal Nature Methods in 2021 and will enjoy using the latest code. But you may not know that the current code is very different from the code at the time of publication. Even if the paper has published, he never stopped pursuing perfection and elegance of the code base. What he did is to rewrite the whole code base to make it modular and user-friendly without sacrificing performance. I don't know how long it takes, but I'm deeply impressed by his dedication. This spirit of doing work slowly and solidly is really worth learning from in this fast-paced and competitive AI research era. Since blindly pursuing quick work can easily lead to some stupid and simple, irrigorous results. In addition, his code has a very strong personal style, especially for the comments. So highly recommend reading nnUnit repository if you want to learn segmentation and laugh at the same time. So today, Dr. Fabian, Isensee, and Max bring nnInteractive, which is nnUnit for 3D interactive segmentation. So without further ado, Fabian and Max, it's yours.
All right, I'm going to take over here, although I can just add to the laudatio that the nnUnit code is actually quite nice, so you should really check it out. But let's go with nnInteractive. So this is our newest project. Shout out to Fabian and also Lars, who's also a first author in this project. And as we had it earlier, there's a plethora of methods out there, right? Which does do this interactive segmentation. And with plethora, I actually mean plethora of methods. And when we first started looking at this field, we thought, well, then the problem is probably solved, right? So you could take any 3D volume, click on it and anything, and then get your segmentation. And this is exactly what we tried. And unfortunately, it doesn't always work. So the methods we compare against always have their sweet spot. They do work, but sometimes you can just do some clicks. For example, on the kidney here, we had just a lovely talk from Vista just right before. But sometimes you have kidneys and it just doesn't work, and you get the same thing for SegWo, for example, in the online tools we tried. So first of all, we thought, well, we're going to do a quantitative analysis of that, and also wrote a separate paper about this. I'm going to spare you the details here, but it's a nice read. The TLDR is basically that, as I said, each model has their sweet spot, but if you benchmark on a large data set of medical data, CT, MRI, and all of this, then you can see that SAM2 still outperforms many of the models. And especially the 2D to 3D problem is a big issue. And we saw this before in the SAMET 3D paper, that 2D to 3D is handled very, very badly for most interactive segmentation models because they don't know if you click on a slice, if is the body meant or is the tumor meant? And then you get these kind of segmentation masks, right? So we need a native 3D model. And this is also why we're really looking forward to this challenge, handling or going towards a native 3D model. Another thing is we want to be open set. So we don't want to suffer from a limited scope, which some other models unfortunately have. So sometimes they are only CT, which was nice at the time. And here you can see, for example, the PRISM model, which is then just for colon, pancreas, or liver. But we want to have a model which can just work right out of the box, which is also super user-friendly. And the last thing is it should be truly interactive. It's about interactive segmentation. You don't want to just place one point or one box, and then that's it. You cannot do any refinement. And since we are also in this interactive challenge now where interactivity matters, that's an important point, right? And before going on about other models now, let's actually talk about nnInteractive. And before I'm showing how the model works, let's watch a quick video. So basically, this is our Napari interactive viewer, where you can just use our annotation styles, which are point, boxes, scribbles, and lasso. And as you can see here, you do a scribble in the stomach, for example, it's half full, it doesn't matter here. And then you do your refinements, right? And this is all publicly available. You can just download it, play around with it. And then you press next object, place a point, boom, the object is segmented. You do the same thing with the box here, one box in a 2D slice, and you get a 3D segmentation. And same for lasso, which is our newest interaction type, where you can just outline the object, and then you have it, your perfect 3D segmentation in 30 seconds. Well, let's take a step back and see how the things work from a methodological perspective. You have your diverse interactions, which are points and boxes, which are quite normal, but also more user-friendly and more powerful interactions, as we'll see later, which are lasso and scribble. Then we have, for those, the two prompt times, which can always be positive and negative, and they are all axis independent. That means it doesn't matter if you're looking axially or coronally or any other axis, basically, it always works. And the last thing, which is really nice, is that everything is open set and modality agnostic. So the model is actually trained on a very, very large data set of a conglomerate of 120 publicly available 3D segmentation data sets. So a huge scale we reached here. And this account amounts to like 700,000-ish individual objects. And this covers CT, MR, PET, and also various targets, of course. So what you would want to see in the end is that you have your initial prompt, which could be a point, for example, and you just click on the object in any slice and it gets segmented in 3D. This is what you want to see here. But what can happen, of course, is that, for example, you place a box prompt and you get a segmentation which is quite good, but then in the end, there's this small part which you miss, and then you just place another point, right? And then you get your 3D object, which is perfect. And this, of course, always applies to other modalities, as you can see with 3D microscopy here, or nnMRIs, which are honestly very hard to see. And then you can do some annotations in one axis, change the axis, and then find out, well, it looks good in the actual axis, but it doesn't look good in the other axis. So then I place a negative scribble and remove that part here. And then you can look at it in 3D and see that even like curved and thin objects really work out well. So now to the nitty-gritty details, right? How does it work? Well, it's actually quite simple, but as always, the devil is in the details. It's of course based on nnUnit. And we had a lovely introduction by Yun on nnUnit, so I guess I don't really have to talk about nnUnit anymore. But we took a very large configuration of nnUnit, which was recently published in the paper called nnUnit Revisited. So I invite you to check that out. And we used this configuration and built a pipeline around the unit, which is basically has a single goal of simulating a human user working with the tool. So what you have here is your image, the previous mask, and then your interactions. And this is also in regard to the challenge where you could really play around with. Like, for example, points are encoded with the Euclidean distance transform, but you could do this with the geodesic distance, for example. I think Strafko has some strong opinions on that, as I heard. And you could basically play around with all of the features here. And what we then do is, if you have a single interaction in the beginning, let's say, I don't know, a lasso or a box here, which, by the way, share the same channel, you put it in the unit, you get your prediction, and then, as Strafko introduced it earlier, you compare the prediction to the ground truth and you find out where is an error region. What we do here is actually we split the error region into false positive and false negative error regions. So we don't have one big error region, but actually split up into false positive and false negative components. And then we sample one of the components from the error regions. And this is then passed to the interaction agents, where we basically have different simulations of humans, right? So this could be the random interaction agent, which always picks a random interaction, as the name suggests, or a single interaction, which kind of stays with the one interaction it chose in the beginning. And then you have your error component, right? And you place another prompt around this error component, which is, for example, a lasso in this case, and the positive lasso, and then you put it back towards the channels here. And what happens here is that you don't forget about previous interactions, so to say. So it's not that you just put the new interaction here, but the old interactions stay in the channel. They get a bit damped, of course, over time. So have less contributions, but the network knows about the previous interactions. And then you repeat this process basically and do this for each and every structure. Just a quick reminder is, of course, instance-based segmentation. So it's always one structure we care about, and try to make it as diverse as possible with many, many structures. And speaking about diversity or generalizability, I mean, I talked about it earlier. We have the huge data set of human labels, but humans only annotate specific things. Humans usually don't annotate toenails, so to say. And this is where supervoxels come in. And we heard about this earlier from the Vista talk, that supervoxels are quite popular in the field of interactive segmentation. But we again looked at previous works on supervoxels. For example, the classical SLIC or Felsen-Swalb algorithms, which is like region growing or graph-based algorithms, or the nice idea of Vista to do this in latent space. And they produce kind of cool supervoxels, but they still are sometimes a bit parcellated, for example, in SLIC, or the borders for Felsen-Swalb were not really nice. So we thought, well, we have all these super cool segmentation models or foundation models at hand. Why not use them? So our approach to supervoxels is actually just use SAM2 and SAM together. SAM produces the initial segmentation in one slice, so this segment everything feature, and SAM2 does the propagation in the z-axis. And this way you get super nice supervoxels. They're of course not perfect, but they're really, really cool. And the code is also publicly available, so you can just use it. It's on the nnInteractive repo, and apply this to the data set of the challenge. Moving on, let's now benchmark the model. And what was important here, if we are calling generalizability in the test and the training set, we also need it in the test set. And we have a large test set of many different and unseen structures. For example, MR, CT, and PET is in here. Then we even have micro CT images of mice, for example, or insect brain, and then the classic organs, bones, lymph nodes, and cancer lesions, and also MS lesions is in here. And if we now apply all of the different models we saw in the beginning of the presentation in our model on this test set with only one interaction, this is the result. So this is one prompt, no interactivity here. Basically, we have one click, one 3D box, or one scribble. And you can really see that nnInteractive does a very good job at segmentation, also just being supplied only with one prompt. And why the 2D models perform better here is that they get more clicks, of course. They get one click per slice. Otherwise, you cannot really evaluate. But still, even with way more clicks, we have a large margin here. But we're not really interested about one prompt, right? We're interested about interactivity. This is where we're going to go. So what you see here is the results with up to 5 interactive point prompts. And you can see that we start off very high and also lead the field in the end with an interactive, which is super cool. But what I want to highlight here, what I found really interesting and also mentioned at the beginning somehow, is that SAM2 is really able to adapt to a new field super quickly. So you have SAM2 here in this turquoise color. It's starting off very badly, but just with a few prompts, interactive prompts, it gets the idea really quickly. And no other model shows this capability. And the last thing I want to highlight about interactivity here is that actually point prompts are the weakest prompts. And this is very interesting and also came with a surprise for us that there's such a large gap. So the highest graph here is actually the lowest in the right image. And you can see that the other prompts, so box prompts, scribbles, and even the new introduced lasso, perform nicer from the beginning on and also reach higher results. So they're just way more expressive. So it would be nice to somehow, like maybe the next challenge, integrate more powerful prompts. And I think I even have a small figure here. Why lasso, for example, is a very powerful prompt, because if you have a box prompt, right, you don't know for the kidney here if the vessel is also of interest. And if it's not of interest, then you have to process the negative point prompt. But if you just do a lasso and give a rough shape, which is just a tiny bit more work, maybe so to say, than a box prompt, it immediately gets it. And And yeah, in the end, here's just some qualitative results. You can again see this effect for 2D models that it sometimes gets it, but sometimes doesn't. And in the end, 3D models here also perform nicely, but sometimes fail for super out of distribution stuff. And for this bounding box, you can see that the 2D models again have this parcellation effect. ZegWall performs nice, and then there's also an interactive. And last but not least, our tool is available not only in Napari, as you just saw, but also in MITK, and the community already adapted it in 3D Slicer, which is really cool. It came out last week. And big shout out to Lars here, who did the Napari integration, also a lot of other work. And with that, I want to thank you and happy to take questions.
This is amazing. Thank you so much for your great presentation. Any questions from the audience? Okay, I may have a quick question. Do you have any suggestions about how participants can beat nnInteractive?
Well, I mean, definitely a very good question. As I was telling earlier, maybe the prompting, like the way how we prompt is not optimal. This is also still an open research question. So not only how we encode the prompts, but what could be interesting and also interesting to us is like where you insert prompt. For example, what we do now is early prompting. So the prompt is inserted similarly to the image, right? But many of the transformer-based methods, of course, do late prompting, which means that you first encode the image and then put in the prompt. And this could be a thing to try. So honestly, there's various routes. nnInteractive is, in my opinion, a very good segmentation model, but of course, there might still be a lot of room to improve.
Okay, thank you.